Welcome to day 3. Today we have the poster session following a session which covers a topic very dear to me and many other graphics people, lighting and night transport. Can you show the schedule? Next night. Okay. Here is the schedule. We have papers 5, lighting and night transport at 9 a.m. And then we are gonna have a short tutorial around 10:50, which is gonna cover similar stuff as the ones that I'm currently gonna speak about. And then we are gonna have the poster session. So now let's go to the actual tutorial. All right, so I'm beaming out to you across the interwebs from our lovely posters gallery hosted on Mozilla Hubs. I'm going to do a short navigation tutorial for everyone that is tuning in and didn't already visit the gallery. You can visit the gallery directly from your browser, mobile device, or VR HMD. Just follow the link posted in the topic of channel posters. You can navigate around using WASD and rotate the view by clicking with your left mouse button and moving the mouse around. To view a poster, you can right-click while hovering your mouse over it. You can also press F while hovering your mouse, and then you can pan the view using the middle mouse button, and you can also zoom in. All right, you can also open a poster in a new tab by pressing space and then selecting open link, and then you can view it normally as an image file. Okay. All right, that's all for now. Come and visit at 11 a.m. Pacific time to learn more about our 4 posters from their authors. And that's all from me. I'm handing it over to the papers chair for the first session. Natasha?
Thank you. So we have a packed and really high power session, as Slavko mentioned, on lighting and light transport, a lot of really fantastic information. And we are going to introduce the speakers. So speakers, please turn on your videos while I do a brief introductions. So Wolfgang Tatzgern will present the stochastic substitute trees for real-time global illumination paper. Wolfgang did his bachelor and master studies at Graz University of Technology, and the paper he'll be presenting arose from his master's thesis. Next, Wolfgang is looking forward to starting his PhD studies. Next author is Tian Xie, who will be presenting our paper, their paper on real-time subsurface scattering with single-pass variance-guided adaptive importance sampling. Tian is a PhD candidate from Van Gogh Lab at University of Maryland, Baltimore County. He is advised by Dr. Mark Alano. His research interests are real-time rendering, game and machine deep learning. He tries to bring innovations to real-time rendering engines to benefit both game and film creation. Next, Christian Luksch will be presenting the real-time approximation of photometric polygonal lights paper. Christian is a researcher at the VR-Viz Research Center at Vienna, Austria. His main research areas are real-time rendering and global illumination with application in architectural design and light planning. He is also working on a PhD in this field. Dachi Lin, who will be presenting the real-time stochastic Lightcuts paper, is a second-year PhD student at University of Utah. His area of interest is real-time ray tracing and realistic rendering. He received his MS in computer science at University of Utah and BS in computer science at National University of Singapore. Lastly, Leung Sen Ge, who will be presenting interactive simulation of scattering effects in participating media using a neural network model, is a researcher at Tencent Technology. He received his master's degree from Shandong University in June 2020 and bachelor's degree from Nanjing Tech University in June 2017. His research interests include rendering techniques and game development. He has done this work when he was in Shandong University. Let's go to the paper presentations.
Hello everyone, my name is Wolfgang Tatzgern and I'm gonna talk about stochastic substitute trees for real-time global illumination. Motivated by Lightcuts and specifically stochastic Lightcuts, we propose the stochastic substitute tree, which uses light probability distributions as inner nodes. Our approach allows us to capture global illumination efficiently over multiple bounces while maintaining or even improve the quality compared to other approaches. In each frame, we distribute virtual point lights and construct our tree over those lights by clustering according to Morton codes, which allows us to support fully dynamic scenes. The tree is then sampled, resulting in a noisy image, which is then denoised and temporal filtered to obtain the final image. As you might have noticed, the paper Real-Time Stochastic Lightcuts is also in this year's I3D program, and we highly recommend you to also watch their presentation. It would have been interesting to compare both approaches, but unfortunately we were not able to include a comparison since it got published at the same time. The most straightforward way to render many light sources is with instant radiosity, deduced by Keller. Virtual point lights are distributed in the scene by tracing light paths from the scene's light sources and placing VPLs at the path's vertices. The scene is then shaded by taking all VPLs into account, and this of course is not the most efficient way and therefore not really suitable for real-time rendering. To cap the number of light sources that participate in shading, Lightcuts was introduced. The rendering cost only grows sublinear with the number of lights, which results in a huge speed-up. Lightcuts constructs a binary tree of the light sources where the inner nodes represent the underlying lights, and such a representative is obtained by picking one of the lights from the subtree during tree construction. Every portion of the output image is then shaded with a cut through the tree, which is determined with respect to a user-specified error bound. But Lightcut suffers from sampling correlation, which leads to temporal instability and causes flickering in the final images. The reason for that is that the light tree is static, so the tree is only built once and is evaluated for every portion of the image. Therefore, it is quite likely that the same representatives, especially those which are at the top of the tree, are evaluated for different cuts, which leads to the sampling correlation. Quite recently, stochastic Lightcuts was introduced, solving the problem of the sampling correlation by replacing it with noise. Stochastic Lightcuts ignores the representatives during the lighting estimation, and instead a random light from the subtree is chosen for inner nodes via hierarchical importance sampling. So, by simply picking a single light sample for each pixel from the light tree via hierarchical importance sampling, we obtain a noisy image, as shown in the image to the bottom right. This noise can then be removed by using an appropriate denoiser. The contributions we make are the following. We introduce substitutes for inner tree nodes that model their light contribution as probability distributions. We show how a stochastic substitute tree can be generated in parallel on the GPU for each frame, enabling real-time animations and dynamic lighting. And we demonstrate how the stochastic substitute tree can be efficiently sampled to approximate indirect illumination. To better approximate the sampling of the in general smooth indirect illumination, we do not use VPL locations for the inner nodes. Instead, we pretend as if the light sources were distributed more densely than they actually are. This is done by merging the VPLs into clusters and approximating those clusters with fitting substitute distributions. In theory, we could use any probability distribution to describe those clusters, but we aimed for a compact and efficient representation. Intuitively, we chose normal distributions, which are described by mean and the variance. We were satisfied with the results and therefore we did not investigate further distributions. We want our clusters to align with the geometry of the scene. Describing clusters that fall on non-trivial surfaces would be costly. Therefore, we try to limit the clusters to surfaces that can be described and sampled easily. The simplest surface, a plane, can be described by position and normal. This actually corresponds to the required information for shading with a visual point light. So, when sampling the substitute distribution, we generate normally distributed samples on the plane defined by the cluster's position and normal. Here you can see a simple example. Let's say we have 4 visual point lights. To obtain a substitute distribution, we compute the density-weighted position and positional variance of the 2 VPLs. As we go further up the tree, the parent distributions are computed by merging child distributions, and this continues until we arrive at the root node. We traverse the tree similar to how stochastic Lightcuts picks the lights for the inner nodes. Based on the illumination from a cluster on a surface point X from the direction omega, we compute the upper bound of LC, which is then used to compute the probability to pick a child. Compared to stochastic Lightcuts, we do not ignore the squared inverse attenuation for the geometry term in case the point to shade is enclosed by a bounding box from inner nodes. We found that this leads to missing color bleeding when using only one sample per pixel, since this makes tree traversal more likely to end up in different subtrees which do not contribute to the color bleeding. In case both probabilities are 0, the surface point is not illuminated by the child nodes. In that case, we simply stop the traversal. While this wastes a light sample, backtracking in the shader to find a node which illuminates the surface point is not feasible for real-time performance requirements. Since our substitute distributions describe the underlying VPLs, we do not actually need to traverse the tree to a leaf node. Instead, we early stop the traversal if we find a distribution that describes the underlying lights well enough. So the tree is traversed top to bottom, starting from the root node until we arrive at the leaf node or a suitable substitute distribution. To decide whether a substitute distribution is suitable or not, we use 2 indicators. The normal metric serves as an indicator for the similarity of the normals between 2 child nodes and the curvature of the surface. μ1, μ2 are the normal metrics of the child clusters, and n1, n2 are child cluster normals. The dot product is lower or equal to 1, therefore the metric is guaranteed to monotonically decrease. The more the normals deviate, the faster the indicator goes to 0. The second indicator is the variance along the plane normal. The variance indicates any deviations along the plane normal, so for example the VPLs may point into the same direction, but they may not lie on the same surface. For leaf nodes, the normal metric is initialized to 1 and the variance to 0. Combining those 2 indicators with suitable parameter thresholds, we obtain a joint condition for ensuring that merged substitute distributions are of sufficient quality for sampling. Here is an example of our stochastic substitute tree. 150,000 VPLs have been distributed from the light source in the scene. The corresponding tree looks like this. As you can see, quite huge surface patches are approximated by a single distribution, which allows us to early stop the tree traversal significantly. We want to rebuild the light tree in every frame, so minimizing the construction time is essential. Therefore, we follow the approach by Karas for building bounding volume hierarchies. To start the construction, we sort the VPLs according to a spatial index using Morton codes. Additionally, we also incorporate bits extracted from the normals, since we want VPLs that point in dissimilar directions to obtain larger substitute distributions. At the end, we concatenate the unique IDs and circumvent any duplicate codes. We thus sort primarily according to position, since VPLs lying on the same surface will be close to each other. Secondarily, we sort according to normals to ensure that VPLs with similar normals are prioritized merge targets. To account for direct illumination, we randomly pick and sample one of the scene's light sources. For indirect illumination, we sample the stochastic substitute tree. For diffuse samples, we stop the traversal at the first suitable substitute distribution. Such a distribution is often found early on, reducing the sampling depth significantly without any visible difference to the final illumination. For glossy BRDFs, we only consider leaf nodes for sampling, thus ignoring the substitutes, since highly glossy reflections would be overly blurred by picking substitute samples. The weights used for hierarchically important sampling of glossy BRDFs use a heuristic which I will describe in the next slide in more detail. So in total we trace 2 shadow rays per pixel, one for direct illumination and one for indirect illumination. For hierarchically important sampling with glossy BRDFs, we use a heuristic which checks if the perfect reflection R of the view vector along the surface normal intersects the bounding box of the substitute distribution. If so, we use R for the glossy BRDF upper bound computation. Otherwise, the BRDF is evaluated with a direction vector R prime, which you can see to the right, which actually does intersect the bounding box and minimizes the difference to R. For denoising, we use a recurrent autoencoder. We reduce the feature count to save some time on inference while still maintaining high quality, but still it's by far the slowest part of our pipeline. To improve temporal stability, we apply a temporal accumulation step from spatio-temporal variance-guided filtering. The blending is controlled by a pixel-wise intensity difference from the CNN output, which mitigates ghosting and temporal lags. Here we compared the performance and quality of picking a single light sample between our approach and stochastic light cuts. The images show the sponsor scene where we distributed 100,000 BPLs. Since a suitable substitute distribution is often found early on, the required tree traversal depth decreases significantly, reducing the sampling time without any visible difference to the final illumination. For shallow trees, which are temporarily not stable, stochastic light cuts is slightly faster for picking a light sample, but as soon as the tree size increases, our approach is always faster. Also, our performance edge increases with increasing tree size, indicating better scalability. We also compared our approach to the lightning grid hierarchy for real-time rendering. Our test setup was a single source point light placed at the center of the sponsor scene. Our approach is significantly closer to the ground truth, faster than the lightning grid hierarchy. The lightning grid hierarchy seems to overestimate lighting in some places while being too dark in others, as shown by the red boxes in the images. We also compared our approach to path tracing. While path tracing with one sample per pixel with one indirect bounce is efficient, it clearly misses out illumination. Path tracing with one sample per pixel and one indirect bounce needs a total of 3 rays per pixel. 1 for direct illumination and 2 for the indirect bounce. Each additional bounce would add another 2 rays. On the other hand, our approach only needs 2 rays per pixel since our substitute distribution already includes the VPLs created by multiple bounces. Here is another comparison to path tracing. The image to the left shows an area light source placed at the corner, which is sampled well with our substitute tree, while path tracing has difficulties connecting the rays to the light source. The image to the right shows a highly glossy T-bot, and although we support glossy BRDFs, mirrors and glossy reflections pose a challenge as sampling with the tree will in general not sample the perfect reflection direction. So, for semi-glossy surfaces, the stochastic substitute tree produces agreeable results, but highly glossy surfaces or sharp mirror-like reflections are better handled separately with path tracing. This table shows the sample timings and final image quality for the different approaches using 100,000 ppls, as well as the potential gains of the different approaches by listing the structural similarity index measure gain per invested millisecond when switching to either technique from the lowest quality approach. The ground truth was generated with path tracing, therefore the path tracing variants may be slightly advantaged for quality comparisons. The columns list the different approaches, so SST is our approach, SLC is stochastic light cuts, PT is path tracing, and the subscript number stands for the number of bounces. Our approach is always faster and achieves better image quality compared to stochastic light cuts, and we attribute our quality advantage to 2 factors. First, using our substitute distributions approximates global illumination as if it were generated with more VPLs. Secondly, our node selection during hierarchically important sampling gives close-by VPLs which have a higher contribution to localized lighting effects higher weight. While path tracing with a single indirect bounce is efficient, the image quality is clearly inferior to SST. In all scenes, there are areas which require multiple bounces to be properly lit. And with increasing number of bounces, path tracing catches up in terms of quality, but requires more time than ours. Our approach always yields the best gains for pure diffuse lighting, and when using glossy BRDFs, we do not sample our substitute distributions. Thus, we traverse all the way down to the leaf nodes, which implies higher sampling timings. So, if you also take glossy BRDFs into account, path tracing performs better. Yeah, to conclude, we presented a new scalable many light rendering approach for global illumination, which supports fully dynamic scenes. And while we benefit from the same advantages as stochastic light cuts, sampling our tree is more efficient since traversal can be stopped early, plus we maintain the same or achieve even higher image quality. We can capture indirect illumination over multiple bounces with a single raycast, while with path tracing the number of needed rays increases linearly. Thank you very much for your attention, and I'm looking forward to your questions.
Hi everyone, my name is Tian. Our paper, Real-Time Subsurface Scattering with Single-Pass Variance-Guided Adaptive Importance Sampling, is a collaboration work with Dr. Mark Olano, Brian Carrias, and Christoph Lugwitz. Are you interested in photorealistic human skin rendering like Digital Mic, the one in Selua's Saga Hellblade 2 trailer and in the Unreal Engine 5 demo? I will tell you the myths in the presentation about real-time subsurface scattering that helps digital characters escape the uncanny valley in real-time rendering. So let's start with what is subsurface scattering. When light shades on a surface, it bounces into the surface and bounces out somewhere else to create a soft look. This effect is subsurface scattering. There are a lot of beautiful subsurface scattering effects in real world that we enjoy, like candle, fruit, and jade. But what we care most in real-time rendering, especially in game, is photorealistic digital human. We long for such a technique that let those characters not only just live in trailers, but in actual gameplays in action. So, why we care about photorealistic digital human? Because we want to escape the uncanny valley. This diagram shows the relationship between the human likeness and affinity. As an artificial character becomes very close to human, it becomes scary. We need to improve the quality to escape the uncanny valley, but at the cost of performance drop. To achieve real-time rendering performance like 60 frames per second, there's three very important challenges to deal with. Performance, performance, performance. So how to be performant to escape this uncanny valley? In this paper, we propose a novel technique. Instead of doing uniform sampling that is not fast enough, as shown in this figure, we perform adaptive sampling to achieve sublinear time performance like this. Before going into the technical details, let's first review how our predecessors tried to clear the thorns of the uncanny valley. Jason and his colleague considered isotropic subsurface scattering in highly scattering media. They introduced dipole diffuse profile into the field of computer graphics for subsurface scattering in 2001. However, for offline renderers only. What sparkles the idea of real-time subsurface scattering is Boshukov and Lewis's work in 2005 for the matrix reload. They use artist-friendly color to blur the gazetted irradiance texture to approximate subsurface scattering. The work back then and his colleague in 2007 brings the realistic part of dipole diffuse profile and the real-time part of using Gaussian filters to approximate dipole together into texture space. It created the first realistic and real-time subsurface scattering for human schemes that matched the offline renderer in the NVIDIA Human Head demo. Eric Penny and George Boshukov in 2011 moves in another direction by offloading online Gaussian sampling into pre-integrated textures. During shading, simple texture lookup based on curvature and shadow parameters is enough. In 2015, the work by Gemellus and his colleague introduces low-rank approximation in screen space to further accelerate the realistic real-time subsurface scattering. In the meanwhile, inspired by Schilling's Fresnel approximation, Christensen and Burley proposed the Burley's normalized diffuse profile that fits all scattering parameters as a whole, which is more accurate than Gaussian approximation of dipole. In 2018, Golubov brought Burley's normalized diffuse profile into screen space in Unity and uses the simple and physically correct counterparameter diffuse mean free path than dipole-based techniques. Due to the expense of brute force monocolor sampling of the profile, pre-calculated sampling and pattern rotation is applied to avoid real-time sampling. However, it's still not fast enough for real-time applications. So here comes our method in 2020. We adopt the simple and more physically correct Burley's normalized diffuse profile. We try hard of a seemingly impossible real-time monocolor sampling by simplifying the sampling function. Bring an offline technique, adaptive importance sampling into real time. We can greatly reduce sample counts required shown in the image. Third, we provide a smooth upgrade from artist-friendly separate subsurface scattering. So, to achieve photorealistic subsurface scattering with multicolor sampling, a typical sampling strategy is uniform sampling. For example, 64 samples per pixel. However, this is too expensive to escape the uncanny valley. When we do sampling, we try to perform adaptive sampling like this and reduces as much samples as possible to increase the performance while escaping the uncanny valley on demand. But how? To achieve this, we have a lot of challenges to resolve. The first challenge we have to deal with is algorithm complexity. Adaptive importance sampling needs to store n sampling histories to estimate samples in time complexity of n to spend in the current frame. We prefer O1 in real-time rendering to not only save memories but calculations. So what is adaptive importance sampling? Let's see an example. If we have 4 importance samplings in the previous frame, and reach an error of 0.02. If we have a target error of 0.01, in the next frame, ideally we need to perform 16 importance sampling to meet the target error. However, this observation of 4 samples per pixel is unstable and insufficient. And when it's unstable, we may result in a large number of samples to reach the target error, which makes us unable to escape the uncanny valley in real time. To resolve this issue, we could perform adaptive importance sampling with sample history. Here, for example, we can distribute the observation in the previous 4 frames. Then, we have sufficient observations to estimate the samples required in the current frame. And iteratively, we can move on for as long as we need it. Let's move on to n-frames and more real scenarios of tool textures instead of simplified construct. We use n-frame history information to estimate the shading of the current frame. Here, for each frame, we need to store 3 channels: the expected shading, the sample count, and the expected square of shading. With this 3 channels, we can estimate the error, and finally do a combination of all history to get the final rendering. However, it requires extreme spaces for caching and extreme time to estimate samples. To resolve this issue, we use tempo accumulation similar to tempo and aliasing TAA for game. The basic idea for TAA is if in the current frame we have a shading, then we can use per pixel velocity to get the projected history in the history buffer of previous frame. After a weighted sum, we can get the final rendering. In this way, we only need to maintain 1 history buffer instead of m. So let's go back to the previous solution. First, We use temporal accumulation to estimate the accumulated effect of shading. In the same way, we can get the expected sample count. Third, however, we do not use a method to estimate the temporal accumulated expectation of shading square. Instead, we directly calculate its variance. To achieve that mathematically, I list the most important formulas here. In our formulation, we only need to maintain one history buffer. To learn more detail of the formula, please read our paper. The second challenge we need to handle is this occlusion due to first appearance and the motion where we do not know the history. So how to sample efficiently without history? Let's see what happens when there is no history. Here we sample the lighting of the center point of an irradiance texture. We show the lighting arrow and the estimated sample count over 150 frames. In the first frame, we do not have history. We could observe that, first, the lighting converges very slow. Second, most importantly, we overestimate the samples. To solve this issue, we use the target quality level when there is no history. It composes of two steps. First, use the target variance if no history, otherwise use temporal variance. Second, use a new shading when there is no history, otherwise use temporal accumulation. With this, let's see what changes for the lighting arrow and sample count. So, lighting converges faster. We also have better arrow estimation. Most importantly, the overestimation has been resolved. The third challenge we want to address is to make this adaptive important sampling technique generic, to make it applicable to other monocolor sampling passes. Here shows the current single-pass adaptive important sampling architecture. It relies on the global TAA pass to update the history buffer. This design makes it dependent on the existing global TAA, which has three drawbacks. It requires a modification of global TAA to output history. Second, the subsurface pass may be affected by other passes like the overlay transparency. Third, at last, the global TAA parameter sets may improve the overall quality instead of for the single pass. To address this issue, we propose a local pass guided adaptive importance sampling. This design decouples the global TAA, which means no global TAA modification is required. And we have constant local quality control, and we could have better quality input to global TAA. Let's take a look at a concrete example. For 2 points in the zoomed-in region, one is in the shadow region and the other is in the flat region, which is the red local arrow and the blue global arrow, for those 2 pixels over 600 frames. For shadow region, the global quality is 11 times better, and the flat region global quality is 2 times better. Our local pass does not constrain the global TAA implementation because we target a lower bound on local pass quality. For example, as shown in this table, we use max weight of global TAA for weight update, while the weight in global TAA is determined by velocity and box clamping. Because of this, people may be worried that this could cause ghosting to the rendering. However, in our scenario, it does cause ghosting, but to sample count. And the sample count ghosting is not rendering ghosting. We demonstrated in this shaking video. This ghosting actually should improve the rendering quality input to the global TAA. And the last challenge we need to deal with is to make the sampling simpler and faster for real-time evaluation. In order to perform important sampling, we need to load the accumulated distribution function and find the analytic inverse and use it for radius sampling in subsurface scattering. However, the inverse is a little complicated. Instead, we propose an approximation which is much simpler and faster. The profile also looks similar. We added our sampling function into PBRT and compared it with the default implementation. We could observe a close match for 2 key samples per pixel in ear and eye region. Here shows our actual implementation of subsurface scattering in Unreal Engine. We show the ground truth comparison between ours implemented in Unreal and the PBRT for Asia Dragon and Infinitive Head Melt model. The adaptive sample count is also shown here. We can see a close match between ours and the ground truth. Our adaptive sample count can capture sample count demands, for example, during the shadow nose region of infinity head. Next, we choose actual performance breakdown of digital mic at 3 different distances. We compared the contribution of adaptive importance sampling to a fixed 6-4 sample per pixel. Our adaptive sampling method contributes an additional overall acceleration from 2 times to 4 times, even considering all the overhead. We got a max of 6 times acceleration in all our test cases. This acceleration is orthogonal to other applied acceleration technique like pre-filtering. Now we discuss what we can do in the future. First, we overestimated the sample count in light gradient change region. Future research can try to minimize the sample count overestimation. The algorithm enables better input to fellow anti-aliasing algorithm. This would be an interesting direction to explore. Future research can apply our technique to other rendering passes, for example, percentage close self to shadow, glossy, and ambient occlusion. There may be also a chance to do real-time adaptive multiple importance sampling. At last, there is also an opportunity to apply our algorithms to offline rendering. Thanks.
Hello, my name is Christian Luksch. Welcome to my presentation of our real-time approximation technique for photometric polygonal lights. Photometric light sources use measurement data to simulate the illumination of real-world luminaires. These kinds of lights are a central component in lighting design and architectural planning. In these workflows, interactivity is a huge benefit. Using real-time rendering system would be very exciting as they provide an immersive experience. However, shading from photometric area lights is currently limited. Our technique provides a suitable approximation to enable these applications. Before I continue with more details, I want to give you some more background on lighting design and the measurement procedure. In particular, far-field photometric data is used. Luminaire manufacturers conduct measurements of the radiant intensity of their products from relatively large distances, which gives the spherical function of the intensity distribution. Such measurement reports can be found as LTT or IS files. They actually do no longer allow to accurately simulate the illumination in the near field. Nevertheless, luminaire models for lighting design tools define the light emission as a polygon or a disk. This provides a practical illumination for lighting design. Here is a screenshot of Dialux Evo, where you see some linear lights on the ceiling and a floor standing lamp. It's possible to depict the luminaire shapes and its characteristic in the near field. But of course, details such as caustics are absent. Actually, luminaire manufacturers try to avoid these, so ideally we get a very similar simulation. For the calculation, typically offline rendering kernels where photometric area lights can be calculated in a natural way are used. The illumination is also often baked, so the camera can be moved, but when the user moves a luminaire, he has to trigger a recalculation, or the image becomes noisy for a short period. Often, you mainly work in CAD viewports without any lighting. Other tools, such as AGI or Relux, are quite similar. This is totally in contrast to the workflow elaborated in game engine editors with a what you see is what you get metaphor. Real-time rendering systems have improved drastically over the last years and adopted physically based rendering with very convincing image quality. Here you see such a system that we have developed in a research project that uses a fast global illumination baking system in combination with selected blending to a real-time preview during interaction. Unfortunately, there is a huge visual difference as photometric lights switch to a point representation. Simplification of the visibility can be accepted, but a consistent near-field illumination would be very helpful when adjusting the luminaire placement. There are already very efficient solutions for diffuse area lights, but arbitrary emission profiles are a challenge. So our motivation is to improve real-time rendering of photometric lights. They should have consistent illumination that allows depiction of the light emitter shape and photometric characteristics in the near field. A closed-form solution similar to existing area light shading techniques would be ideal. Our technique focuses on polygonal lights with a low number of vertices, as this seems to be the most important use case. The smoothed illumination in the near field should make an approximation possible. First, let's have a look at how the rendering equation of a photometric area light is defined. For simplification, we have already excluded the visibility and assume a diffuse emission, with ρ divided by pi moved out. In difference to diffuse area lights, here the polygon defines a field where the light is emitted from with the measured radiant intensity. You could also say that we need to calculate the illumination from a collection of point lights equally distributed on the polygon. We also make the illumination independent from the actual size of the polygon by dividing by the area A, as the photometry defines the absolute emission. As you can see, we have a division by the squared distance to the point on the polygon. In order to increase the effectiveness of our approximation, we transform this to a hemisphere integral. This is usually the preferred strategy as it makes sampling more efficient and uniform viewed from the point to shade. So we project the polygon to the hemisphere and integrate the radiance LE over the subtended solid angle omega. In case of a diffuse light, LE would be constant and could be moved out. With a photometric light, it is dependent on the incident direction omega I, and it's derived from the radiant intensity by dividing by the area A and the cosine of the outgoing direction. One issue in this formulation is that it no longer allows the expression of light emission within the plane of the polygon, as it degenerates when projected and the dot product becomes zero. We can also expect numerical artifacts close to the plane when the photometric light should emit in that direction. It's actually not that uncommon that photometric lights emit within the polygon plane, but it turns out that this issue can be worked around by some tweaks. You can find the details in our paper. So we have the simplest possible expression to calculate the shading from our light. As we strive for a real-time approximation, it would be only reasonable to use a very simple scheme. Therefore, we will take a look at two techniques used with diffuse area lights. The first is structured sampling. The idea there is to approximate the integral with uniformly spaced samples. If we use the corners and the center, this works very well for a diffuse light. Doing the same with a directed emission, the sampling pattern becomes visible close to the polygon. This is not very pleasing. However, at medium distances, we already get a much better approximation than that from a single point. We only need to find something better for the very near field. Another technique approximates the illumination from a single dynamic point, called the most representative point. This point is constructed using spatial heuristics and is depending on the point to shade and the light orientation. Ideally, this gives the average of the illumination. As you can see, it works very well for diffuse lights. As there is only a single point, it's always pattern-free. Unfortunately, with a directed emission, there often is a noticeable gap or offset in the illumination. The intensity is also biased towards the one value that is sampled from the photometry. We experimented with both approximation techniques in all kinds of variations. One observation is that the closest point is the most important for depicting the shape of the light emitter in the illumination, but of course it becomes too bright. It became clear that we need a strategy that combines the strengths of both. Our approximation technique uses fixed samples, in particular the corners of the polygon, to cover the entire integration domain, together with the closest point as dynamic sample to reflect the shape of the light emitter in the illumination. The only question is, how do we calculate the integral with arbitrary samples? Or more precisely, what are the proper sample weights? One solution is to build a triangulation and perform a piecewise integration that we will refer to as curvature. Ideally, you would use a Delaunay triangulation, but actually any triangulation can be used. We decided to build a triangle fan around the closest point. In case of convex polygons, this will always provide a valid triangulation. This is how the curvature looks in general. It's a weighted sum of the average function values at the triangle corners, and the weight for each triangle is the spherical axis or solid angle. So if we put in our shading equation, we get this. I've shortened the expression and restructured it to the radiance times a geometric term. This can now be calculated straightforward in a pixel shader. One issue that we can already expect in the geometric term is that the point at the horizon plane of x, where n.omega I is 0, will no longer contribute to the approximation, and also close above the plane the radiance weights will be quite uneven. The resulting illumination will then look like this. Note that I've moved the polygon even closer to the ground to emphasize the issue. You can see a drop in intensity here. If the polygon would touch the ground, the near field would even become completely black. Nevertheless, this is already a huge improvement. So let's go back to our curvature. We chose to modify it slightly. We decided to separate the calculation of the average triangle function value to the product of the average radians and the average geometric term. And this is now the final shading calculation of our approximation technique. One case I did not mention so far is where the polygon is only partially above the horizon plane of X. We handle this in the overall shading procedure by first clipping the polygon to its visible part. This might introduce an additional edge or degenerate to a single triangle. In any case, the triangulation will provide appropriate weights. Back to the scenario from before. It now looks absolutely plausible. In direct comparison to the reference, it's a bit too bright and the illumination outline is too wide. But without, you might not be able to tell the error. One of the most important properties is that we do not see any discontinuities. With this dataset, we have actually already chosen one of the more challenging ones. Let's see how our approximation performs in a variety of other scenarios. This photometry has some noticeable spikes. With our approximation, you can see some structure in the near field. This is not exactly how it should look like according to the reference, but it's not disturbing and the error is quite low. The way we decided to implement the curvature is absolutely robust when the polygon intersects with a surface in all kinds of orientations. The next luminary emission looks quite smooth, but actually the spherical function is somewhat rectangular when viewed from the top. The real model would also have a linear shape and not a square, but for our evaluation we used this normalized setup. Again, the approximation works quite well and only shows very little structure, and there are no issues in any special case. Now let's jump to real lighting design scenarios, where the luminaires have an appropriate geometry and the emitting polygons are modeled accordingly. This line tick has a very thin shape and is one of the extreme cases. When moved parallel to the wall, limitations of our approximation become visible and some irregularities can be seen. Our method only combines a few samples, and when the closest point moves along, intense changes in the measurement data will produce a pattern. The panos looks flawless. Note that we here also render hard shadows using cube shadow mapping. The illumination is absolutely smooth and it's one of the best overall. Next, we have a luminaire that also has a weak emission in direction of the polygon plane wrapping all the way to its back. You can see some illumination on the ceiling. Our approximation produces a continuous illumination while the luminaire is moved through the ceiling. There are also no artifacts when intersecting the wall from the side. Our tweaks to handle the singularity that you can find in the paper do not introduce any issues. Here we are back to the slot light, the second luminaire you saw in the beginning. I delete the other two so you can see the illumination more clearly. In real scenes, texture and structure on surfaces reduce the visibility of patterns such as you could see previously. Here, the illumination does not show any conspicuity. A lighting designer would actually avoid most placements you see here. They should demonstrate the robustness of our approximation. Now we are at the luminaire model of the first dataset you saw in this video, the mirror. As you can see, it's quite detailed and the polygon that defines the light emission is actually hidden. So when we move it close to the wall, there is an inconsistency between the model and the illumination. This is the best rendering that we can get out of a photometric measurement and absolutely sufficient for lighting design. There, the major concerns of lighting designers are that illumination levels on tables and floors are met and that the spacing between luminaires is sufficient to create a uniform illumination. Our approximation finally provides a solution to enable real-time systems to be used for this kind of application, allowing a completely interactive workflow. Last, I want to show some performance numbers. The times were measured in the most simple possible setup, without visibility and no tone mapping. The baseline is a single fixed point representation. Our approximation runs at reasonable additional costs. Shadow mapping and other effects typically used in real-time rendering application would usually make most of the frame time. At the bottom you can also see times of a Monte Carlo method with 8 solid angle samples, with and without denoising. This also runs more than fast enough on an RTX 2080 Ti. I refer to our paper for more details. To conclude my talk, our approximation enables real-time rendering systems to be practically used in lighting design and other applications with photometric lights. We have demonstrated that our method works robust and without disturbing discontinuities on a large dataset. It's also easy to integrate in a rendering pipeline as it does not require any additional passes or preprocessing. In our paper we also propose an extension for specular shading based on the linearly transformed cosine technique. Thank you for your attention. Follow the link below to find a demo and supplemental material.
Hello everyone, I'm Dachi Lin, a PhD student from University of Utah. Today I'm going to introduce real-time stochastic lightcuts, a real-time main light algorithm. This work is a collaboration with GEM-UXL. Dealing with main lights is very common in real-time rendering. This includes modeling real lights or using virtual point lights for approximated global illumination. But handling main lights can be quite a challenge due to its computational complexity. Traditionally, game engines handle scenes with main lights using a mixture of baking and tile-based lighting. However, this method cannot handle both fully dynamic scenes and unbounded light influence ranges. Recent works have lifted these limitations by bringing Monte Carlo sampling for main lights to real time, thanks to ray tracing capable GPUs and high-quality denoisers. Dynamic main light sampling, a real-time version of adaptive tree splitting introduced in HPT 2019, is a method that samples lights from a light tree constructed using surface area orientation heuristic. This light tree has high sampling quality, but is also expensive to fully rebuild, leading to their two-level solution. Restir is a main light direct lighting method introduced in this year's SIGGRAPH. This algorithm can give high sampling quality, but it's currently limited to the shading of primary hit points. In this work, we present a new Monte Carlo real-time main light method called real-time stochastic lightcuts, which uses a light tree that is extremely fast to build and traverse. This can improve the overall sampling efficiency. Our method is an extension of stochastic lightcuts, an offline main light method introduced in 2019. The core of our method is the use of perfect binary trees for light sampling. On top of that, we also introduce a novel weight computation scheme of light tree sampling, and a technique called cut sharing to reduce computation overhead. As a quick background introduction, our method is based on stochastic lightcuts introduced by UXL in 2019. It belongs to a group of recent offline main light sampling method inspired by the 2005 Lightcuts paper. Given a set of scene lights, the stochastic lightcuts build a light tree by clustering lights hierarchically. Different from the original Lightcuts method, stochastic lightcuts does not use representative lights, but instead randomly sample a light from a cluster to compute the lighting of that cluster. This eliminates the structural error caused by lightcuts. Given the shading point, it starts by forming a cut below the root. To sample a light for the root cluster, it stochastically scales down the tree to pick a light. At each level, it selects a branch with a probability calculated using some weights related to the cluster lighting estimation. This is also known as hierarchical importance sampling. In this example, we finally pick the red light, and this red light is used as the light sample for all internal nodes in this path. Similar to Lightcuts, the maximum possible illumination or illumination error bound is computed to determine if the cut should be refined. This error bound is determined conservatively by things like minimum distance to the cluster bounding box, sum of light intensity in the cluster, and so on. In this example, the error bound is above the threshold, so the cut is refined by moving one level below, and child node that has not picked a light does the same hierarchical importance sampling to pick a light. This process is continued until all nodes above the cut are either leaf nodes or their maximum illumination error bound is below the threshold. Because lights are sampled, at each execution, a different set of lights will be used for lighting estimation. Notice that light samples are weighted by the inverse sampling PDF. It's easy to see that stochastic Lightcuts eliminates the sampling correlation by randomizing light selection. The result is that it can perform temporally stable lighting estimation using a very small cut size. Since it doesn't use any representative light, it also doesn't have any restriction on light types. But one thing that can make stochastic Lightcuts problematic for real-time rendering on GPU is the tree construction cost. The light tree is built by agglomerative clustering, which can be difficult to parallelize. Depending on the scene, the light tree can also be very unbalanced, causing thread divergence in sampling. However, unlike the original Lightcuts, stochastic Lightcuts allows using any tree, which can also be built deterministically, because its unbiased sampling is not dependent on tree quality or tree randomization. So here we introduce real-time stochastic Lightcuts that features perfect binary trees. A perfect binary tree is a balanced, full, and complete binary tree. This condition is satisfied by filling zero-intensity bogus lights to make the number of scene lights a power of 2. It is constructed like this. First, we compute the Morton code of the quantized light positions. Then we sort the lights along the space-filling Morton curve. This gives us a set of lights that can be easily clustered by spatial proximity. We then append bogus lights to the sorted list of lights to make the number of lights a power of 2. Then we form the internal nodes above the leaves by simply merging pairs of lights. For each internal node, the bounding boxes and intensities of light child nodes are simply added together. Bogus lights or bogus nodes are excluded from the bounding box computation. This gathering process is repeated to form all levels. Since this gathering process is fully deterministic and commutative, we can generate any level directly from any level below it, and this means any combination of levels can be generated in parallel. A perfect binary tree allows extremely fast construction, making it suitable for real-time rendering of dynamic scenes. On the other hand, it has high sampling performance, which compensates for the loss of tree quality. Factors of high sampling performance include the balanced topology, which allows implementation to exploit better computation or memory behavior. Also, no charging pointer is required for traversal. Besides the simple perfect binary tree, we also provide an option to use a two-level perfect tree to improve quality for scenes with sparsely distributed light meshes with heterogeneous sizes. More details can be found in our paper. To sample a light, we need to traverse our light tree by hierarchical importance sampling. The weight for selecting a branch is related to distance to the light cluster, but it is tricky to define a distance that does not cause problems like infinite sampling weights, which can happen when the distance is 0. Here, we propose a different strategy. We compute the sampling weights using both the closest distant dmin and farthest distant dmax to the cluster bounding boxes, and average the probability in these two cases to get a probability of picking a child. This avoids the common singularity problem while approximating the expected distance to the lights in cluster. More discussions can be found in our paper. Compared to the weight formulation in the original stochastic Lightcuts paper by Yüksel, our new weight computation gives a minor but visible improvement in sampling quality. Another thing we did to increase sampling efficiency is cut sharing. Cut selection can be expensive if it is done for each pixel. However, we can amortize this cost by computing a cut for a group of pixels, by observing the fact that nearby pixels often share the same cut. To compute a cut for a k by k block of pixels, we randomly select a representative pixel and use the corresponding shading point to select the cut. This process is done for all pixel blocks in the screen. In the second pass, we fetch the pre-computed cuts and perform light sampling such that each pixel in a block share the same cut, but samples from the cut independently. Here, we compare the different cut sharing block size k. Using k equal to 8 provides the best balance between sampling speed and error. This is the scene we use to test different block sizes. Notice that sampling results with cut sharing can include visual artifacts near depth discontinuity, but after spatial temporal filtering, it produces indistinguishable filtered result. The additional benefit of cut sharing is that it naturally enables interleaf sampling. The core idea of interleaf sampling is to partition all light sources within a pixel block such that each pixel in the block only evaluates a subset of the lights. The result produced by this method can be reconstructed with a filter. The cut sharing method we propose enables us to use interleaf sampling for light cuts. Without interleaf sampling, each pixel needs to sample from all light clusters in the cut. To do interleaf sampling, we partition the light clusters on the chosen cut to distribute them evenly over the pixels in the interleaf sampling block. In this example, each pixel receives one cluster, reducing the light sampling cost to 1/4 of the original. In this example, using only 8 light samples leads to high sampling variance around the red light, but using 2x2 interleaf sampling increases the effective number of clusters sampled by each block to 32, which approximates the quality of 32 light samples per pixel. Here's the image after filtering. An additional improvement we did is to rotate the light cluster assignment of pixels within a subblock, so that the same pixel does not get the same clusters every frame. This allows achieving better quality with spatial temporal filtering. That's all of our method. Notice that by default, we do not use interleaf sampling in our results, since it requires filtering to get rid of the structural error. Now let's see the results. Our results are generated using our RTX 2080 GPU. More configuration and implementation details can be found in our paper. Here we present the light tree construction time using two scenes. One contains 100,000 VPLs, the other contains over 10,000 emissive triangles. Our tree construction takes only 0.43 milliseconds and 0.15 milliseconds on GPU, respectively, which are more than 2 orders of magnitude faster than agglomerative clustering on the CPU. Notice that the actual tree construction of building levels is so cheap that sorting becomes the most expensive step. Here, we compare our method with dynamic magnetite sampling or the real-time version of ATS in the quite expansive scene. Notice that given the same sampling time of 22 milliseconds, our method can generate more light samples than ATS and produces a result with significantly less noise. However, since our tree has lower quality, ATS produces a result with lower error with the same sample count of 11, though it uses much longer sampling time. Notice that our light tree construction is also orders of magnitude faster than ATS in this scene. Because a completely new set of VPLs is generated in every frame, ATS has to fully rebuild the light BVH, which is expensive. Here, we compare our method with ATS using the Cornell box scene with a few animated mesh lights. The ATS builder is much faster in this scene, since it only needs to build the top level tree. In comparison, our method fully rebuilds the light tree in a shorter time. Our method also achieves lower error given the same sampling time. Here we compare the filtered results. Notice that there is still obvious low frequency noise with ATS after filtering, which is not seen in our results. To understand more about the sampling behavior of our method, we compare our perfect tree to the unbalanced tree built by agglomerative clustering. We also compare with a sampling strategy that picks all light samples from the root node without using light cuts. Here we show comparison at equal sampling time of 30 milliseconds. In the quite expansive scene, our perfect tree with light cuts generates the result with the lowest MSE. Also notice that method with light cuts achieves lower MSE than method without light cuts, but all these methods produce lower noise than uniform random sampling. In the Cornell box, we have the same observation. However, it's not always the case that the perfect tree produces lower noise than unbalanced tree. In this scene, unbalanced tree with light cuts provides the best quality. This shows the performance gain of using a perfect binary tree may not always offset the potential reduction in the tree quality. In this bistro scene, we use a 2-level perfect tree. While it slightly increases the sampling overhead, it is still fast and produces the best sampling quality with light cuts. In conclusion, we have presented a real-time light sampling technique for scenes with many lights. Our method extends stochastic light cuts by using a perfect bounding light tree with a novel weight computation scheme and cut sharing. By minimizing the cost of light sampling, our method allows using more light samples within the same period of time for achieving higher sampling quality. We discussed the limitation of our method in our paper. For future work, a direction is to explore important sampling of light clusters on the cut. This is done in many offline many light sampling methods, but it requires experiments to see if it improves the real-time sampling efficiency. Another direction is to reduce the sampling evaluation cost like shadow ray tracing, which is not a part of the tree traversal, but could be a non-trivial cost when the number of light samples is high. Thank you for listening. The paper, code, and video can be found with this link.
Hello everyone, welcome to our talk about interactive simulation of scattering effect in participating media using a neural network model. Here we have two mediums, oil and milk. For the participating medium, the lights emitted from light source enter into medium and scatter many times before leaving the volume. We have different medium here, so how do we describe them? In our paper, we only consider homogeneous medium, which means each position in the volume has the same properties, and we use absorption coefficient, scattering coefficient, and the phase function to describe a medium. In the left image, the single scattering contributes the most, so we call it low-order scattering dominant. In the right one, the multiple scattering contributes the most, so we call it high-order scattering dominant. In our paper, we divide the scattering event into three types: single, double, and multiple scattering. For multiple scattering, we simulate a lot of scattering effect in the medium, which is very expensive. In our paper, we focus on the simulation of high-order scattering, both double and multiple, and use an approximated method to calculate single scattering. Before starting our approach, let's review the related works briefly. Photon density estimation is one way to solve the radiative transfer equation. The basic idea of these methods are shooting photon points or photon beams into medium and compute radiance to camera ray by photon density estimation. But all these methods need to store a large number of photons. Another work is based on Monte Carlo sampling, just like virtual ray lights. In this method, the light emits rays to the media and the rays do random work in the sun. Then, these rays are used to compute the multiple scattering for the camera ray. However, this method cannot handle single scattering. In this image, the caustic are missing. Diplo-based methods are very efficient at representing multiple scattering effects in high albedo material, such as Diplo BSS-RDF, directional BSS-RDF, and so on. These methods encode multiple scattering response into a surface function that can be queried efficiently. However, in this method, the material responses are not accurate. Wang proposed a pre-computation method to solve expensive multiple scattering. In the pre-computed stage, they put a point light in efficient media and shoot a large number of photons. For multiple scattering, we store their radiance in relative position in the table. After process of pre-computation, we can directly get the radiance from the table in the rendering stage without complicated computation, which can be applied into several algorithms, such as VRL, UPBP, MELT, and this method is fast compared to previous method. However, this method costs expensive memory and need material-specific pre-computation, which is a big problem for the GPU implementation. Note that this method is basic of our work. Based on above discussion, our goal is to interactive multiple scattering rendering of arbitrary homogeneous media with less than 100 means per frame. To achieve this, our method relies on pre-computation. More especially, our approach includes compressed representation with neural network, pre-computation for the entire homogeneous material space, efficient simulation of multiple scattering in VRL at interactive rate with GPU. Before starting showing our approach, we would like to show some final result first. In the video, we can see that our method could render multiple scattering at interactive rate. We first define a radiance function. This function represents the radiance that the multiple scattering events contribute to the camera ray. The rho and z represent the scattering effect position. Theta and phi represent the outscatter direction, and g and alpha represent the medium property, albedo, and anisotropic factor. And we treat it as a regression problem. For this regression problem, we use a 2-layer neural network with 50 nodes each layer to learn multiple scattering function phi. The input has 6 parameters, and the output is multiple scatter contribution. Our method has 3 steps. First is training. In this step, we train a neural network to represent our radiance function, and then, as extraction step, this step is used to pre-compute segment table. Finally, the rendering stage generates VRLs and renders the final results, not only including multiple scattering, but also single, double, and surface radiance. First is the training step. Here are the main settings of our neural network. Here we show some result of our neural network. Here is the radiance lobe representing the radiance distribution at different directions with a fixed space position, and these lobes are obtained directly by pre-computed method, and the lobes in the right are reconstructed from our network. We can see that the lobes generated by the neural network are similar with the actual ones, and these color meshes represent the radius distribution at different space positions with the same direction. From the comparison, the difference of our network is not obvious. After training a neural network, the next is the extraction stage. Using network directly in rendering is a straightforward method, but it is slow. Therefore, we reconstruct a radius table for specific medium in advance. Each element of table represents the multiple scattering contribution of a light ray to each sample on the camera ray. To estimate the entire radiance of a given camera ray, though we have a reconstructed table, it still spends much time doing sampling in scatter position on camera ray and querying elements in table many times, which is costly. So, we use a further operation to pre-compute. First, we assume a given camera ray is fixed, which is fine because we can ignore the contribution of samples that are far away from camera. In practice, we found that forming free path is a good choice, and accumulate radiance for each samples. Based on this, we could get a segment radiance table. Using this table, in real-time rendering stage, we just need one calculation to get an entire camera ray's radiance. For camera rays, which is not full mean-free path, we use a weight based on actual length to scale radiance. In the rendering stage, we compute direct illumination and store the first segment inside the medium into a buffer. We use VRL for our rendering algorithm. The light source emits virtual rays into participating medium. These rays will be scattered or absorbed. The orange lines are reflected by boundaries, and blue lines are created by scattered. In the actual generation, we only need store orange lines and omit blue ones, because their radiance for camera is included in segment table. Then, we organize all generated VRLs into a uniform grid. The resolution and interval is decided by the mean-free path of a given medium, and then transfer grid onto GPU. After generating all VRLs, we trace ray from each camera sample and compute direct illumination and store the first segment inside the medium into a buffer. For the second step, we downsample scattering illumination with one sample per 2x2 tiles as multiple scattering trains to be smooth. We compute the multiple scattering radiance via the use of thread. Each thread gathers the computation made by the grid cell to the pixel, and discards grid cells during the traversal if the solid angle subtended by the cell and the camera ray is smaller than a predefined threshold. Of course, the acceleration structure based on tree, like BVH or tree KD and so on, might be another choice to organize all VRLs in GPU, but in practice, we found the tree structure is unsuitable for GPU concurrent and our core scheme is slow. The results are rendered on this platform. And we compare multiple scattering only, double and multiple scattering, and full solution in our result. This figure presents a comparison between our method, one's method, and VRL, and the reference image is computed using UPBP. Only multiple scattering results are displayed. Our method produces pictures that are virtually identical to the reference image and is faster than the Variance method and VRL. Those three figures present the different scattering components in our method. Increasing the number of scattering components increases the computation time, which goes from roughly 50 ms per frame for multiple scattering only to roughly 150 ms per frame for the full solution. Note that in our paper, we don't consider the indirect illumination on diffuse surface, so there is no caustic phenomena in this figure. For this dragon sun, we zoom in on two interesting areas, a thin area on the ear and a thick area on the body. We find that our method with full resolution works well in both cases. Here are more results. This is a candle sun. This is a fog light sun. Our method still has some limitation. First, we cannot guarantee energy conservation. Second, for materials with low albedo, the performance is slow. In conclusion, we have presented a compact model to represent double and multiple scattering events in the participating media space. The method is easily combined with many existing rendering algorithms. Finally, our method could get highly efficient GPU implementation. Thank you for your attention.
Hello. Thank you all so much for listening to the presentations, and many thanks again to the authors and the presenters. In particular this year, they had to do the extra work of putting together these videos, and the wonderful thing is you'll now have these videos for reference for far, far longer to make the implementations of these papers that much easier. Now we go into the Q&A session, part of the session, and we have a few questions queued up. What we'll be doing is we'll be asking specifically to the authors. If there are more questions, please go to the Discord channel or the YouTube chat and ask there. Please specify if it's for a specific author or for the entire panel of authors. So the first question is for Tintin Xie. How this technique, importance sampling specifically, can be implemented in a real-time game engine?
Hi. We implement our technique in Unreal different rendering pipeline. So you can use the pixel shade path, and after we have finished it, and we switch to compute shader, because subsurface gathering is not everywhere, and we can use the indirect dispatch to further accelerate it. Yeah.
Perfect. Thank you. The next question is to Wolfgang Tatzker. Could you share how large K by K pixel blocks you use for the results, and what effect the choice of different K has on the quality versus performance?
So K by K pixel blocks. So for each pixel, we sample the tree only once. So actually, we don't have a K by K block. So I'm.
Got it. Must have been a confusion from the authors.
Maybe this is for Dakilin, because they use something like that.
That's in our paper.
Maybe. Okay. Apologies, misdirection. Can you please expand upon that?
I think that's in our talk. We have a result showing that, and I presented that in the talk.
Okay. The next question is for the Leong-Sen. In the demonstration, there were some artifacts around the triangulation. Is there some negative values not being clamped, or is it inherent artifact of this technique? Could you expand upon your intuition behind that?
Because it need a lot of time and for get interactive rate in GPU, we make a lot of approximations to multiple scattering. So you can see that in the front video there are some artifacts which is for save time.
Thank you. Okay, the next question is, it was mentioned, sorry, this is again to you. Can you expand on the limitation of the technique due to low expected performance for materials and how this could be integrated to a generalized material pipeline?
Oh, sorry for the question is for me.
Yes, I'm sorry. Yeah, to Leong-Sen.
Oh, sorry for my poor English.
No, it's okay. I can go slow a little bit. Effectively, the question was related to the mention of the low performance, expected low performance for materials with low albedo. How would you work around that in a generalized material pipeline?
Yes, we have a limitation on low albedo material, but we just focus on the high order scattering material, and we think that method can be applied into both of high order scattering, just like milk and candle. So we think that our method is good in the entire homogeneous space of the dense material, dense media. Yes.
Thank you. That's helpful. Next question is to Wolfgang. Could you expand upon the limitation of your technique? For example, how would the reuse of light cut within a pixel region impact the quality of the node selection?
So with reuse, I guess you mean something similar like cut sharing, I guess. Yeah, so with only one sample per pixel from the light tree, I guess this wouldn't really work with our approach. Because all the pixels in the block, so to say, would use the same subtree. So yeah.
Thank you.
So you wouldn't get illumination on different subtrees. All would use the same subtree. We would have to use more samples, like in the real-time stochastic light cut method.
Thank you very much. So the next question is to Leong Sen. It was mentioned that energy conservation could not be guaranteed. How would you work around this?
Energy conservation.
That is the question, part of the question.
We don't, this is a great point, but we don't, to address it. We think that the energy conservation is not very important for our method to simulating multiple scattering. We can, from the result that though we don't get the energy conservation, we still have a greater result.
Thank you for clarifying. So the next question is for Tintin Xie. Could you expand on the performance breakdown for the variance guiding phase, since this is the near fixed cost that's being added to the renderer? You're muted. Could you unmute?
Hi. For that cost, yeah, it is fixed and be a small portion of the actual rendering. And so you, for subsurface scattering in real time, you usually have a theta pass, and then you do subsurface scattering, and then you combine them together. And so here we have the theta pass and the combined pass that is constant. And with using our indirect dispatch, and we can further accelerate it. And apart from this, we have actually another cost is pre-filtering. If you read the paper, which built the map for the irradiance texture per frame. For that one, it's another fixed cost, but it's like it takes very small portions of the subsurface scattering. And for subsurface scattering, the only time that when you demand a lot of sample is like you have high line gradient changes. And in that situation, and the constant cost can actually be ignored. Yeah, that's my answer.
Thank you for providing more details. Okay, we're kind of coming up on the shortened answer questions, but the last question that's piped in is for Dachi. Could you clarify the approach you use for rotating the light cluster assignment within a subblock?
So I think I've also talked about this in my presentation. So the purpose is to enable every pixel to have the chance to select all the lights when you have across many frames. So it's the rotation means basically there are it means that a pixel will get the cluster assigned to its neighboring pixel in the next frame. And if you have k big pixels in a block and in k frames, each pixel will sample from all the k clusters. And just yeah, I think it's pretty clear in my talk. Yeah.
Thank you. The next question is also to Dachi. Have you tried using a wider tree instead of a binary one? Do you think the trade-off with having a shallower traversal might be worth a more expensive evaluation at each level?
I think that's a good idea to try. Yeah, so far we only see light trees that are binary, but for wider branching factor, I think it depends on. I think it depends on the actual performance. So we need to try that. Yeah, but that's an interesting idea.
Thank you very much. Okay, well, we've settled on the questions thus far, so we're gonna finish up the Q&A session. To all watching the stream, please note that we have a Discord channel dedicated to this paper session. The authors will be still able to answer your questions in the Discord channel, so please feel free to keep asking. You can learn far more about the techniques. Reach out directly. And to authors and presenters, thank you so much for all your hard work in giving us more explanation behind your work. It is deeply appreciated. And I know it's been quite a lot of work to put this together, so thank you very much. Have a good rest of the day, evening, and afternoon, wherever you may be. Take care.
All right, folks. Welcome to the I3D 2020 poster session. I have a few announcements to make before we actually start the session, so get around. During this session, we are going to give opportunity to our authors to present their recently completed or work in progress projects. First, I would like to go over the controls and do a short demonstration. I have a bit more time than what we had in the welcome session, so I will be slightly more thorough this time. So please follow the instructions on your screen to learn the navigation controls. They're shown as blue message bubbles, but essentially you can use WASD for navigation and click your left mouse button to rotate the view on your computer. On mobile, use pinch and drag to navigate, and on VR HMDs, use your thumbsticks to walk or trigger to teleport. Make sure that your microphone is turned on and correctly set up on your browser so that you can directly speak with the authors. You can view posters by right-clicking on them and holding F. And while holding F, you can pan the view with your middle mouse button. You can also open a poster by holding space and then opening. And then you should be able to view it normally as before. And on mobile devices, you have to two-finger tap and then you can open link. On VR HMDs, you can use X and then open link. So that's pretty much it regarding controls. Make sure to spread out between posters if you are a conference attendee so that the authors have time to chat with you. I also suggest that authors attend their posters at all times. We have a soft ending of this session in about an hour, but you can stay as long as you want. During the session, I will go to each author and ask him a few questions so that our listeners on YouTube can get an idea about his work. Now that you have this information, we can truly start the session. So spread out and enjoy the poster session. Okay. All right, folks, you can go to the poster's authors and ask them questions. All right, I'm gonna go to the first one. So, okay.
Okay, hi.
Hello, Backdash.
Okay. Yeah, can you hear me?
All right.
Okay.
Let me be sure that I'm next to you so that I can hear you well. Okay.
Okay, should I start?
All right. So, hi, can you please introduce yourself and tell me a little bit about your work? Make sure to state your affiliation.
Yes. Okay, so my name is Backdash and I do independent research under the banner of Too Much Will Do Software. So today I'm going to be presenting hybrid ray voxel tracing fixed capacity grids. This is basically my replication of Crytek's Neon Noir ray tracing technique in Vulkan API. Although the technique is not really limited to Vulkan, you know, there are analogs between everything it uses in other rendering APIs such as DirectX 12. In my implementation, I basically do not have any requirement or dependence on geometry proxies, so that's what is rather unique about my technique. So at a very high level, it actually is a lot like uniform grids with one major exception, and that is that every grid cell basically has a fixed number of references that it can hold, a fixed number of triangle references that it can hold. So basically, overall, the technique is broken into 3 parts. So there's one part that handles static geometry that doesn't happen very often. There's the part that handles dynamic geometry that happens every frame, and obviously there's the part that we consume basically all the artifacts produced by these two parts to produce a ray trace scene. So starting off with this handling of static geometry. So initially, it just starts off by creating the grid. Every cell, every reference in the grid is initially set to FFFF. That's our magic number for blank references. So then it proceeds to actually handle static geometry. So you can see these two triangles representing basically static geometry. You can think of them as triangles belonging to the, let's say, the columns in this cathedral. So we're going to focus on this cell specifically over here that I'm highlighting. This table refers to this cell. So you can see there's one static triangle overlapping the cell, and you have its reference inserted here. And moving on, every frame it tries to basically get rid of all the dynamic references in the grid. And the reason it does that is because, well, in literally the next step, it has to basically reintroduce dynamic references. So it does this by looking at basically the instance IDs, first 16 bits, the instance IDs of each reference, and if they're equal or greater to the number of static instances that are in the scene, it just blanks them back to FFFF. So then it goes on, and you can see this red triangle. This you can imagine as being a dynamic triangle belonging to one of these animated teapots, and it just basically introduces it into the grid. And you can see the table for the cell over here. It now has two references. It has the static one and the dynamic one in red, and there's still room for more references. So the rest of them are still FFFF. So move on to basically the consumption of all the artifacts that are produced in these two sections. And basically, it just handles it just like any uniform grid application. You know, you have a ray segment that's cast into the scene. It just keeps traveling until it hits a cell that has you know, non-blank references. Now, there is one major addition here, and that is that if that ray segment comes to contact with a cell that has all of its references saturated, all of its references taken up, and it does not produce an intersection, it actually takes the last interacted or last encountered rather triangle within that cell, and basically blows it up and reports a virtual intersection with that triangle. And that basically is to fill holes. I call it gap filling technique. That is to basically fill holes when we actually have cells that are rather saturated and they have holes. This is to basically give the perception of information when there's lacking information. Now, this actually introduces a problem that if you bounce off, if your first bounce is off of the surface that is already saturated, you might self-intersect. And the way that is handled is that basically at your first bounce, it casts a shadow from the ray segment onto the normal surface that you're bouncing off of in, say, the G buffer, and it basically does a division to basically see how many steps minimum it has to travel in order to avoid self-intersecting. And only after it's traveled that many steps, it actually kicks in the gap filling technique to avoid self-intersections. And that basically allows us to basically have, you know, because these teapots are actually fairly dense, but it allows us to basically not have self-intersection on the teapots while still getting, for example, you know, self-reflections on the teapot as well, with for example, the opening over here. So that is the technique in a nutshell. The scene parameters are currently basically picked you know, via trial and error. This is something that we'll address in future revisions. But since I have to actually get these in a very manual sense, I've actually posted the parameters here. And basically down here, I have the results. One of things that are interesting to note is that on an RTX card, at least on the Sponza scene, it came within 30% performance of RTX on an RTX card. Now, granted, this isn't basically functionally equivalent to RTX, but it is rather functionally similar. So results like that are rather interesting. So with that, I basically I close my presentation for the poster. I wanted to emphasize that I'll be available for live demos, you know, source review and tweaks and stuff like that, one-on-one. So I encourage you to walk up and ask me for that after. So with that, I'll be taking questions. Thank you very much.
Okay, we actually have a few audience members around here, so does anyone want to ask a question right now?
Cool, so you're getting around 10 minutes.
Okay, I'll ask a question. you can think about your own questions. How does your technique differ from previous works?
So basically, the main thing is that the gap filling technique in the sort of self-intersection avoidance that I described basically obviates the need for having proxies. So if you actually read the Crytek Neon Noir presentation, the way they handle basically really dense scenes is that they basically have the geometry reduced by a proxy, and they ray trace against the reduced geometry, against the decimated geometry. This is not always viable, and in the fast forward demo, you can actually see me causing procedural destruction. And in a situation like that, it's just not feasible to really produce proxies in real time. So this basically obviates the need for proxies, so it can handle situations like that, basically trivially rather.
Okay. Anyone want to ask a question?
One of the strong hypotheses that prevented us from using.
All right. I'll ask another one. What are the viewing distance constraints of your technique, and how would you avoid popping of detail if it's limited to just a small space?
It's basically the largest scene that I think I've supported here is actually Sudantic. The thing is, the way to handle this, for example, for open scenery and things like that, is to sort of use a clip map style. Have a fixed grid around the viewer, and basically after the viewer has traveled a certain amount of distance, you can just basically clip the entire grid again around the viewer and just basically do that. Now it might introduce a little bit of a hiccup, but it will be able to basically support larger scenes. So that's how I would handle open scenes with this technique. I would basically just do this clip map style.
I'm just still wondering whether make noise for the other.
Any more questions?
Yeah, I have a question.
Yep.
Have you experimented on implementing this using the RTX or hardware ray tracing? For this looks pretty similar to the Zvogi Crytek thing.
Sorry. So the engine actually does have an RTX pass. That has an RTX code path. But the thing is that a lot of these numbers over here are actually on Radeon 7 that doesn't even have RTX, and that's what this technique is really for. It's for cases where
it's hardware agnostic.
Sorry?
Yeah, it's hardware agnostic, right?
Yes.
Yeah.
And
so I was specifically asking if
RTX comparisons down here as well.
I'm sorry. Yeah. May I ask my question?
Yeah, go ahead.
Yeah, so I was wondering if we can accelerate this using hardware ray tracing.
This is specifically to do this where hardware ray tracing isn't available. If you have hardware ray tracing, I would say use hardware ray tracing. This is for the late generation GCN cards and the first generation RDNA. Like, I would not try to say mix this with RTX in any way.
Got it. Thanks.
No worries.
All right. Anyone else want to ask a question? Okay. I'll thank the speakers. So thank you, Backdash, for your thorough explanation. It was a very interesting work. And I'll move now to another poster. I'm going to number 4 because the 2 other ones get issues logging into hubs. So basically, we are gonna do them separately on Discord. All right. Okay. UI.
Hello, Josko.
Hi. Can you please introduce yourself, state your name and affiliation, and tell us about your work?
Sure. So I'm Elie Michel. I'm a PhD student at the computer graphics group at Télécom Paris. And the work I present here is about rendering sand in real time. So our main goal in this work was to be able to play with grain level sand interactively, which means we would have to need sometimes to really see close grains individually, but also have many grains at the same time on screen for further views. So it's a complicated problem because of the amount of geometry it would make, and it's more generally a level of detail problem. And because the grains are really thin structures, with traditional mesh simplification wouldn't work, because it would just make all the grains completely vanish. So we had to find something else. And another strong goal that we had was to be able to move all the grains individually. So we couldn't pre-compute anything related to the position of the grains. But the good thing is there are also hypotheses that we can make to solve this problem, and the main one being the low number of grain shapes, because all the grain basically have the same shape, and by shape I mostly mean the silhouette of the grains. The color itself can change, but what matters is that the visibility issue is always the same. And because all the grains have similar shapes, and also because the shapes are spherical enough, we'll also use this, and they are densely packed together or close to densely packed together, we can efficiently use impostors to draw intermediate scale. So for it's a multi-scale model. So for the closer grains, we use meshes. For further grains, it's just points. And what will interest us is the intermediate view, to have an intermediate model that matches both in between. And this model is based on impostors. So the impostors are what they are. Technically, drawing the impostors is a point-based draw call. We draw screen space little quads, but in those quads, we use views that we pre-compute before. We pre-computed in the first pass. So this here is the shape of the grain, the original shape of the grain. We pre-compute it from many different views, and what we store is just those pre-computed views. And then when rendering, we just reuse those pre-computed views and splat them on screen at the right position and also at the right orientation. And another thing is that we don't directly splat the final color of the grains. We actually store intermediate representation, the G-buffer representation, because this way we can have dynamically relate the grains, and in particular we can have all the grains have different orientations, which makes it okay to have always the same shape or a small number of shapes, because if they are randomly rotated and randomly colored, for instance, it's less noticeable. So we actually have G-buffer impostors rather than simple impostors. And in trying to draw a lot of impostors of the same shapes at once, we also had to take care about the order in which we draw these impostors. And we actually split, this is here, we split all the buffer of grains. So in the first pass, anyway, we split all the cloud of grains in a couple of parts. So the closer one are just meshes, further one are points, and the impostor ones are actually split in two parts. We keep the closer, we draw the closer one first. This way, almost all the screen is already filled with the final their final color, not color because it's a G-buffer, but their final pixel values, because we know that those were the closest grains. And then we fill the remaining points with all the other points. And this way you can see in this these curves, the speed up induced by just the fact of splitting one draw call into two draw calls for the impostors. And another speed up we worked on was to in the splitting process, we actually discard some of the grains when we know for sure that they will be hidden. So it's occlusion culling, but it's occlusion culling that happens before actually knowing the exact shape of the grains. We don't look into the impostor's map at this stage. We discard them prior to this, and this is where we also use the hypothesis that the grains are round, are spherical enough. Then we can know for some grains that they are totally hidden without knowing actually, without querying the impostors. And so overall, with this approach, we were able to render a much larger number of grains at the same time, and also have the transition from meshes to impostors be as seamless as possible. And because we also study at which distance it is theoretically needed to switch from meshes to impostors to be able to not notice the transition.
Okay. Should we
If you
ask some questions?
have any questions?
Okay. Excellent. We have plenty of people here. So does anyone want to ask a question? Okay. All right. I have my own question. So sand and other granular media is often translucent and light can reflect multiple times before impinging on the camera sensor. So basically how light transport works. So do you have a solution that compensates for multiple scattering inside and outside of your sand particles?
We didn't explore this yet for this model because all of this was already required to solve the primary visibility problem before solving the multiple scattering of light in the sand. But so it could be complementary further work. And yeah, I know that for offline rendering, this is the primary concern of people working on sand. But for real time, we already had to solve the first part.
Mm-hmm. Okay, thank you. Does anyone else wanna ask a question?
Can you hear me?
Can you come closer?
So my question is the findings of this poster applicable to grass rendering?
To grass, you'll have the problem of sphericity. So a grass strand is not spherical at all. But the impostor based method would work anyway. It's just that, for instance, all the other culling mechanism wouldn't work. And also, the impostor we design here is in the way at render time we query the maps, the pre-computed maps. We make the hypothesis that the grain is close enough to sphere or sphere based, and this is also something you'll have to change to apply to something which is really not spherical like grass.
Okay,
thanks.
Can I ask one question? I guess I will sort of ask this again. Yeah, so have you basically experimented with sort of adaptively, like for example, a very large scale, let's say a big desert, with many square kilometers of viewing distance, sort of blending between sort of a BRDF approach and your imposter approach, and like how to draw the lines between the sort of the LOD levels and things like that. Have you experimented with that?
I have mostly focused on this transition and so this one and the one with further model than like the one you mentioned that could be here, and the skin would are still left to exploration. This is really something we could do, but for this, I guess would have problems with the hypothesis that the grains can move individually. Plus, it doesn't really make sense to think about individual grains when they are really far away. So maybe you would have to also redesign the way you express the dynamic of the sun for those far views, and maybe depending on the way you express the dynamic and you model the dynamic of the sun, maybe this would induce a way to render the sun as surfaces, because maybe it's going to provide you a surface which we don't have here with just the hypothesis that as input to this method we have a point cloud. So for BSDF based approach, you would need a surface, and maybe you could just mesh the point cloud, but maybe you could tie it together with the other parts of your pipeline.
All right, thank you.
Anyone else want to ask a question?
I have a question. Yeah, how are you handling the glitter that we see in sand? So are you doing something special to handle that, or does the material provided implicitly handle things like that?
The idea is that since we populate the G buffer, then all the shading stage can still be resolved in the same way the rest of your render engine works. You might have issues for the furthest views at some point, and this is related to the first question. Actually, for the furthest view, you'll have issues, filtering issues, because you will have many grains in the same pixel, and at this point you'll have aliasing issues. But for the impostors here, then once the impostors are rendered, the results at the deferred shading stage is the same as if it would have been meshes.
Got it. Thank you.
Anyone else? Okay. I think that we're good for now, but you can always stay around and ask the author some other questions. I'm gonna just quickly check the other posters. I'm not sure whether the authors are in Discord. It's gonna be slightly more awkward, so I'll stay in the room and basically look at the poster. But for the voice part, we are gonna use Discord. So basically, make sure to log into the posters channel. There is the voice posters channel, and then we can basically get voice from there. Okay, I'm moving to poster number 2.
Yeah, I can't tell who can hear who though.
Okay, we have an author here. Hi Matt, can you hear me?
Got really quiet because he walked far away from us.
Yes, I can hear you. Can you hear me?
Okay, excellent. Can you introduce yourself and basically state your name, affiliation, and tell me a little bit about your work? Just make sure to be short. We have time for questions. Okay. Yeah.
My name is Matthew Key. I'm from Cal Poly in San Luis Obispo, California. I'm presenting today a poster based on a animated short that I and 19 other students worked on during a quarter session about a year ago. And it's based off of the Into the Spider-Verse movie. We wanted to see if we could, in a 10-week period, as a group, collaborate and focus on different rendering techniques to put together something cool. So this is what we ended up with. And we were each split into teams working on different rendering technologies and graphics effects. A couple of the ones highlighted in this paper are a global illumination system, a chromatic aberration for a glitching effect, some comic book panels, and a cartoon shader that you can see on the far right with the pig spider.
Okay. So obviously that's a project that multiple students participated. How was the work split between students? How did you put together the final video?
So in the beginning, we sort of thought about what different scenes we wanted to animate, and we actually thought about that before we ended up writing the script. But once we figured out the different technologies, each of us split up into our own groups based on our interests.
Mhm.
And once we had teams set up, I was actually tasked with putting the script together, and then sort of putting together a storyboard that we would all follow along with. So we all use the same rendering engine, written mainly by Colton Yeager, the first author of the poster. And to put it together, towards the last couple weeks of the 10-week period, we worked closely with Colton especially, but also with whoever else was in our respective scenes, to sort of pool all of our technologies together in the necessary ways. For example, the comic book panel technology needed to work with the people who developed the shaders for the other 4 characters as well, so that the alpha maps didn't conflict with the shaders. And that's just one example of that.
So that was put together in a common code base, and then you basically worked on your respective scene by sharing code, or did you develop it a little bit on your own?
There were a couple people that they developed their own technologies, but then later on they would come in and collaborate with the engine, the person who wrote the engine, or someone else, and then each group would render out their own frames for their scenes, and then in the end we would stitch them all together to create the short, which I have a YouTube link to in case the link on the poster doesn't work.
Ah, okay. So make sure to post it in the posters channel so that other folks can see it and basically get a more idea about your work. Okay. So let's see whether anyone here has questions. That's quite an interesting work. Some people are involved in teaching, so I guess that it's quite an interesting opportunity for them to learn about how other people perform their duties and how the students actually feel about those projects.
So yeah, I had a question for you, Matt. Just yeah, I was wondering sort of how you, well, the trick with a lot of non-photorealistic stuff is that it kind of can fall apart under various conditions. Did you sort of, you know, tell the artist don't do the following, or did you just sort of modify algorithms as you went, or how did that go, or did everything just go smoothly?
Things definitely didn't go smoothly. Like you said, there wasn't as much uniformity, I should say, with, like, for example, with some of the models that we developed. Some people needed to change sizes, for example, of some of the models to fit with certain effects. And in the end, once we had already stitched everything together, we found some of those differences didn't matter as much for the end result, but when it came to continuing work on the short, like for example, I and a couple other people wanted to re-render the entire thing using the global illumination scheme. But this wasn't as easy as it should have been because we didn't set some of those uniformities in place. The couple of uniformities that we did have in place had to do with the engine itself. We all used a Blender for the modeling, and then we all used a custom written GLTF importer for the graphics engine. So that provided some challenges, but it also made it a little bit easier for everyone to work with the same engine.
Yeah, oh, cool. Yeah, no, right. Yeah, I forgot about all those other challenges, like yeah, tools and formats and all of that stuff. Yeah, I'm sure there was a ton of fun problems. You, if you had it to do all over again, or someone else on to do a project like this, what would you, what's your sort of number one or two things like? Make sure you do this up front.
I would say because the rendering engine was somewhat in progress at the beginning of the quarter, I would say have a rendering engine ready ahead of time, because this was sort of a let's see if we can do this sort of collaborative effort. But as time went on, the engine would evolve with our needs. But I would say set up what technologies you need ahead of time, develop the engine in that way. And then another problem we had was because there were so many different students with so many different graphics backgrounds, not all of them understood the code the same amount that for example, the original developer did. So I would say have more of a solid base code to work off of that is easily understandable by everyone else.
Okay, thanks.
Yeah, sure.
Anyone else want to ask a question?
Hi, Matt. So, could you elaborate a little bit on the green screen process that you mentioned over here using OpenCV? Seems interesting.
Yes. So that particular process was used for the cartoon shader in the pig spider. That individual used Blender to model the pig first with different colors, so that of course the shaders could take over those different colors and map the different things on top of it. As far as the green screen process for that cartoon shader, I can't speak so much about the script itself. I can link you to the report that student wrote up. But as far as what I know, after the sort of green screen parts on the pig model were generated, every single frame would be fed into the script, and then the script would generate a pink pattern with white dots all over it, and then it would only overlay spots with pure green, like a green screen. And then once that was done, it would feed the frame back into our rendering engine and overlay that on top of the pig to give it the polka dotty outline.
Got it. Okay, cool. Yeah, that makes sense. Thanks.
Anyone else want to ask a question? Okay. Do you have any thoughts about how the process can be improved? Like basically the collaboration between students?
I'm sorry, can you repeat that?
Do you have like any thoughts about how this process can be improved? Basically the collaboration between different students?
Yeah, I think, like I mentioned earlier, the having a more solid rendering engine in the beginning definitely would save some time, because I think we spent 2 or 3 weeks just making tweaks to the engine and having people learn the engine.
Yeah.
And even then, people still had questions throughout the process about the engine itself because it was so complex. So I guess to that end, it would also be useful to have more than one person who is as experienced with the engine, because that one person who developed it was stretched very thin between everyone's questions. So I would say having more than that one person to answer engine questions would be useful as well.
Okay. So do you have any experience with other frameworks that are designed for teaching, not like Real Engine or like Unity or Unreal, used in that kind of setting where students are contributing on a project? Do you think that it's a better idea?
I have experience with Unity and
But-
a little bit with Unreal Engine, but not so much. We specifically wanted to move away from game engines because, I mean, in one aspect, the professor wanted to give us a challenge and keep it quote unquote like code pure and give us that experience. But definitely, if we were given the option to use a game engine instead, I think we may not have learned as much, but perhaps it would have come out either faster or in a better quality. But I mean, it's all about the learning experience, and I think all of us learned a great amount from this.
Yes, my only concern about this idea is that if you want to develop like advanced effects like the ones that you are showing, it might be more difficult for the students to navigate humongous code base like Unreal or Unity. That's my only concerns. But
right, that's definitely a concern that we ran into some problems with that, but we sort of just worked through them. Yeah.
Okay. Thank you. Yeah, that was quite an interesting conversation. Do we still have anyone that wants to ask a question? Okay. Seems that no one wants to ask a question on stream. You can always ask questions afterwards. The authors are gonna stay until the end of the session. I think that we have about half an hour, so yeah, feel free to chat with them. So now let's move to the third one, and it seems that we also have the author here. So we are not gonna do the awkward setup with Discord, so that's great. So Ritesh.
Hi, can you hear me?
Can you hear me?
Can you hear me?
Awesome, thank you. So can you introduce yourself? Basically
Yes.
state your name and affiliation and tell us a little bit about your work. Just make sure
So
that
my name
you're
is
sure. Oh, okay, thank you.
Yeah. Okay. My name is Ritesh Sharma. I'm a PhD student at University of California, Mercer, and on this work I have collaborated with Professor Kamal Reyes and Professor Marcelo Carmen. And the work is about 3D behavior for multi-agent simulation with position-based dynamics. So what happens is collision avoidance is one of the key components of multi-agent simulation for both 2D and 3D. Most of the methods are available for 2D and can be extended for 3D. But when these collision avoidance works, they work in a planar environment. Like even though they are working in 3D, they behave in 2D. So what we wanted to do is like introduce a concept called separation plane. So basically a separation plane is a plane where collision happens. Okay. So what we do here is like we have just extended the PVD 2D PVD for curve simulation to 3D, and we have used the same method as the existing method. Only the step which we have changed is the step 4. If you can see in the PVD, the solver, this is solving long range collision. What we did here is like we use the same method to find our display collision normal. So if you see the black color arrow is a normal to a plane, and the plane is here. And then what we do is we take one of the axis, global axis. So if you want to do it for horizontal, you will take y-axis. If you want to do it for vertical, you will take a x-axis as your g-axis as your vector. Then you take the corresponding of normal and the chosen axis to get a vector, which is a blue vector. That's a collision of direction. After you have a collision, you avoid. And then what you do is like taking the blue vector and the green vector or yellow vector, whatever you take the resulting sum to get a predicted velocity. And that's how you avoid the collision. In the figure below, you can see here is like this is horizontal collision avoidance. If you see from a top view, you can see it's moving away in the horizontal direction. If you see the vertical collision avoidance, how does it work? You can see it here on the sideways. So it's avoiding vertically. And this is a comparison with the RVO, which is a well-known method for collision avoidance. There are some more results here. You can see here. And why this is important was because if you are trying to simulate UAVs, you want UAVs to go sideways rather than going top and down. But if you have a planes to simulate, it can go top and down as well. So it gives some more control to provide to the animator to simulate real scenarios, and it can also be used for motion modeling. So yeah, that's what I have.
Okay. So I guess that I can now ask questions or
yes.
let other people
Sure.
ask questions. Does anyone else want to ask a question? Okay.
Actually, I have a question. I couldn't hear anything the presenter just said.
Oh,
but
really?
I hear you fine.
Did you stay close to the presenter?
Standing right here at poster 3, but I didn't hear anything.
You have to be close because there is proximity out here.
Yeah,
I have one question.
I can barely hear the. Okay. Hello.
I'm sorry.
Can I go ahead?
Okay.
Oh. Okay, yeah. So I just had one question. So basically, this would apply to situations where you have sort of when you're simulating the automated agents, right? Like you have control over the simulation, correct?
Yes. Yes.
What if you're dealing with systems specifically because one of your motivations actually mentioned drones? What if you're dealing with situations where you have a bit of an open system where you have other agents sort of interacting with your system that you don't have control over? For example, if you have drones, let's say, coordinating in space, what if, for example, a flock of geese show up? Like, have you considered how to handle those situations where there are agents that show up that you don't really have control over, simulation control over? How would you handle those sort of emergent scenarios?
Yeah, so we haven't talked about this yet, but like definitely can be done. Like, so right now we are picking planes based on global axis, right? What we can do is like we can have some algorithm to find out the flock of agents at some position, and then we can find a plane which is just orthogonal to the agent to find the direction of the movement of the agent. So mostly what we do is like algorithmically we find where the agents are, and then we can have a control.
Yeah, I can hear everyone except the presenter, it seems. That's interesting.
Okay,
can you hear me? Can I speak again?
I can hear you.
Okay.
So it's probably on his end somehow.
Okay. So can I actually? So that's actually interesting. I wanted to sort of then extend the question actually because this is very interesting. So for example, with basically trying to say use some sort of open CV situation to try to approximate like the 3D positions of the individual sort of birds within the flock, and then trying to, for example, apply some sort of real-time PCA or SVD approach to find, for example, the plane. Like, would that be, I guess, an interesting vector to look into for situations like that?
Yes, definitely.
All right, thank you.
Anyone else want to ask a question? Okay, I have my own question. So have you considered different shapes of your agents? Because I would imagine that a plane cannot do a certain maneuvers compared to a quadcopter.
So can you repeat the question? I didn't understand the question clearly.
Should I repeat my question?
Yes.
Okay, so my question is basically, have you considered agents that have different control surfaces? Like, for example, a plane and a quadcopter, they probably have some constraints on their basically navigation skills, so they cannot do certain maneuvers. Have you considered that sort of constraint in your project?
Yes, yes, we can do that. That's the reason we choose position-based dynamics, because these all the collision avoidance happens based on constraints. So you can add those constraints to make it work here.
Anyone else want to ask a question? Okay. All right. Do you actually handle other geometries than spheres? So
Other than spheres, yeah, so it's possible to do more. Like sphere was the simplest example that we can think of to start with, and we are considering for different shapes also.
Okay. Anyone else want to ask a question? Have you considered also non-planar collision avoidance, such as a flock of agents orbiting a single target?
We haven't talked about that. That's possible. Yeah, that's possible, but we haven't talked about this yet.
Okay.
It's just a preliminary work that we are presenting now.
All right. Anyone else want to ask questions? All right. I think that the scripted part of this session is over, so you can go around and chat with the authors. I'll also look at some questions on Discord, and I'll ask the authors so that we get answers on YouTube. So yeah, feel free to go between clusters and chat. All right, that's it.
I just wanted to say I'm still available for live demos if anybody would like to.
Oh yeah, Backdash is gonna do a screen sharing near his poster and show you his technique. It's something that he wanted to be mentioned. All right.
All right, thank you.
Oh, and another thing, we might have also researchers around just gathering surveys. So if they ask you some questions, don't be confused. We actually allowed them to gather the survey data. Okay, let's look at Discord.
So my question is like, what is point-based drawing? So hard.
So you mean this one here?
Yeah, that's fine.
One thing to mention, if you want to view full-size posters, just hover over them, open, then code space, choose open link, and then you're gonna see a PNG of the poster, so you can view it in your browser.
Basically, it means that so in my attempt, this is by far, compared to the other parts, the one that has the most left to improvement. But for my experiments, I used a model in which I keep only a small layer of grains, of the grains which are closer to the surface, and I draw them, I blend them together, so I draw them additively, so that to reduce the aliasing. But basically, it's point-based rendering, so just draw points, and I keep only a shell of grains.
I see. So do you use any noise there, or is it from rasterization by?
Any what? Sorry.
any noise texture?
No, it's just there's rasterized points. There's already too much noise at this stage. So, but what we use the noise for?
You see,
So, I mean,
you have anything from YouTube?
every single point go to like rasterize.
Okay,
So
can
how
anyone
many
see my
million
screen
points do
share?
you rasterize?
Okay, we don't have questions on YouTube.
I went up to 20
Previously we
million
saw, but
points
it's gone now.
for the scene on the top
how about
right
now?
corner. And for this, the scene, the view wasn't 60 FPS. It was
Really?
Just check
interactive, but not real time.
what's going on around, because it's probably quite interesting.
Wait, it's sharing, so you can't see it right now? Let me try one more time.
You see the posters.
Let me
But
see.
it was already possible to move around in the view. And I'd say
I'll
that
just share entire
for,
screen. Oh, wow. I don't know what happened to it.
million points, I could
Okay, let's see.
Can,
How about now?
Oh, there it is,
can I help you
Alright.
to set it up so that everyone can view it? Or you can do it on your own?
Let me. Can you see my screen still, or did it?
Yeah, we can see
Okay.
your screen.
I don't know what happened. Okay. It's
Can
weird.
we just and watch it a
There's-
little bit?
Yeah, no, not for tens of millions of points. But for a smaller number of points, the game is still.
Oh, there we are. So it's just loading. Just give it a second. Okay, so now I have more scenes than this. I have all the scenes in the poster. Just let me know. There's Spawns of Sabenic. There's which one was it? Yeah, the fireplace. There's also a gallery scene that takes 30 seconds to load.
Okay.
There's all that stuff. So yeah, feel free to ask. This is like I was kind of planning this on being sort of a one-on-one thing. So, and then I can do tweaks. I can show source code if you have like questions regarding any specific part. You can go through it, you know. So yeah, just feel free to ask.
Can you do Spawns demo?
Yeah, for sure. Just give me a second. I actually have source tree. Okay, it's still there. Perfect. So let's give it a second. Oh, okay. Let me just apply. Let's see.
This is a fun process to watch, I have to admit.
Thank you. All right, so I've just stashed these just in case. So I need to actually change a few of these parameters because it specifically spawns us. So just give me a quick second. Let's see. Yeah, it's too much for spawns. So that's that. And I'm gonna also get rid of this. And we're gonna go here.
I think your screen is gone again.
Oh, just one second. Let me just tweak these things. I'll bring it back. And let's see. Just a quick second. So wait, the screen share is gone? No, it's still. Is it? I'll just share again.
Yeah, because you had two up before. There's one black one, but there was a second one that was working.
I don't know. It just keeps disappearing for some reason. All right.
There it is.
Something where someone shuts it down. Please don't. All right. So just 1 second. We run Spear V Optimizer. Okay. Shit. Just get rid of them. Perfect. That should be spawns now. Oof. Oh, let me actually make it non-full screen because I'm going to lose the browser and everything.
Oh, there's exception.
Just give it a second. My computer is genuinely slower because of the stream thing. This is, I guess it'll have to do. Okay, so let's just bring this over here because Vulkan won't render outside. Or at least the final pass won't. Okay, just give it a second and it will be there. Spawns is a lot bigger than the other one, so I hope it's still, ooh, trippy. Yeah. No, there we are. I can this can actually do more than one teapot. I can hold on. Let me actually just quickly. I just noticed I'm just doing one teapot. I can do 3, so I can push this even further. So let me uncomment these because these won't fit in the fireplace. That's why I commented out. Go.
Hi, can you hear me?
Barely.
We are Georgia Tech students, and we are doing our master's project about social VR for conferences. So, do you mind us to ask you a couple of questions?
Sure, go ahead.
Yeah, so we are going to ask you some questions regarding today's poster session. And can we ask, why do you come to this poster session?
Well, for me, I'm coming to present a work I've been doing. So the poster you see here, which is about, so it's a work I've done. I actually started this work during the end of my master's degree, and then first year of my PhD.
Cool. And how do you compare this virtual poster session to those traditional physical ones?
It's a bit disturbing at first, but it gets much smoother than I would have expected at first, I'd say. It's still possible to talk with other people in a relatively spontaneous way, which is what is important for this kind of session.
So those horns
and do you have any suggestion about how this can be improved?
These are particularly really dense.
One thing I was thinking of is that it would be convenient to be able to have somewhere in the screen the name of the people talking when they talk.
But everywhere else where you can see, that the triangle density is not that high, you can see it's pretty much, ray traced. So that's basically the advantage of the techniques. I guess it's how it deals with like excessive density and keeping a cap on intersection costs and things like that. These teapots are really excessive in terms of their triangle count compared to everything else. I kind of get really close. You can see kind of voxelites. Sorry?
The screen disappeared.
Oh, it disappeared again? Okay, hold on. Let me just do this one more time.
Than the posters.
Thanks for letting me know. I have no idea.
Yeah, maybe about the posters or just network.
Is there like a time limit on this thing?
I think the poster actually spawned elsewhere in the room.
Okay, gotcha.
Oh, oh, my poster? Hello?
It moved now, but it was over by the door when I came into the room.
Oh dear. It keeps disappearing for some reason. But anyway, so yeah. So anyway, for anyone who hasn't seen, so I'm gonna try and like get really close to this so you can see. Yeah, so you can see again those pikes are kind of voxelized again because of like high density, triangle density for the parameters that we chosen, but everything else is pretty much triangles. Yeah, and the teapots are at least for our parameters like pretty high resolution. But I can also show another scene, fireplace, where the parameters are just perfect for the T-bots, and basically I can just turn off the whole gap filling technique, and it'll just look really great all around, whether it's the scene or it's the T-bot, or just everything all around looks pretty much like RTX. So anyway, I think Eric wanted to see this. I don't know if he's still here.
So if you want, continue to keep in touch with the person
Oh,
to get to know
hello,
different processes
Eric,
and
you there?
they try to
You wanted to see sponsor, right?
I didn't ask, but I'm all for it. I know sponsor too well.
Okay, somebody asked. I thought it was you. Somebody asked for sponsor. I can do other scenes. Sorry?
Yeah, so are you
That's
working
my way of getting.
to be a full paper something, or
This was a full paper. I guess I don't know. It wasn't convincing enough. I guess I don't know. But there are aspects of this that I do really want to build out on. Specifically, the whole gap filling. Right now, it's basically just a linear interpolation. But one thing that I was really excited about, and I see some people are kind of stumbling upon it, is using sort of like small little autoencoders for tiny cross sections of the environment. Sort of like having these autoencoders that represent implicit surfaces. So you have like a really tiny topology. It's a few weights, and it represents a sort of an implicit surface representing a very tiny cross section of the scene, one of these tiny voxels, and that would be actually fairly interesting as a means of filling sort of incomplete information. You can like say, feed it like 10 triangles or something like that, and it'll just like give you a nice little continuous implicit surface. So that's one interesting avenue that I've been thinking about, and I see actual publications coming out like right now tackling stuff like that. There's like mini deep SDF kind of situations, and those are super interesting. I could build out more on that. So yeah, that is certainly interesting.
I have to admit I have an ulterior motive in asking, and just in that I know that I'm not involved directly with it, but I know Ray Tracing Gens 2 is the call for participation is still open. So and they're actually looking for sort of, they can look, they're sort of the full-blown paper kind of things, but they're also just looking for little techniques. Like if there's just some little like, ooh, I don't really want to write a whole paper about that, but I have this cool thing that is worth, telling people about. That might be a thing you might consider without too much effort. Anyway, that's my ad.
Yeah, actually, I was thinking about that. I haven't built out on that as much, like I haven't explored that space and did that tiny little interest. I haven't like built out on that as much. If I had built out on that, I would most certainly like write something that kind of collects my thoughts on like, hey, like here's all these various ways that you can sort of tackle, like tiny bits of geometry in voxels, like beyond voxels, how to deal with sort of incomplete information, in a very tiny cross section of space. You have like implicit surfaces, you have this sort of gap filling thing. I've been also been thinking about textured voxels. Like voxels, folks tend to use like at most in games, for example, they tend to use anisotropic voxels with each face having a different color and like a different normal and so on and so forth. But you can have like a voxel that basically has UV information along with it on each face, which basically is again really related to this, because if you get really close, I don't know if you can see it well, I can show it in the other, it's a lot easier on this other reflector. So you can see like those pipes are actually textured voxels. Like it's not just one static color, and that actually helps with the perception of ray tracing, in this. So even though like some of them are really like voxel in shape, there's more information. So it might basically trick the eye to think that no, it's actually the full geometry. Well, it's not. It's a simplified shape, but it's textured, so it gives you that more sort of variety and variance. It says to think that it fools the eye better.
Yeah,
is what I'm trying to say.
Yeah, exactly. That's ultimately that's the goal. Yep.
Right. Yeah. It's all trickery.
That's right. Well, I mean, as a Jim Blinn said, it just has to look right. So, you can.
Right. It's perception. It's all perception. Right?
It's easier if it's using PBR and science and so on. But if if need be, we everybody has to make some kind of we're not shooting 10 gazillion photons per second. So.
Right.
Yeah. Yeah. No. Anyway.
Yeah.
Well, like I say, I definitely encourage you to anything you feel like, oh, I just want to share this cool little idea, consider ray tracing gems or journal
for sure
techniques, or there's a lot of
sure.
sort of practical journals out there, like as opposed to the latest greatest far in the future kind of stuff. So anyway.
Yeah, actually, I don't know if you've seen, I did this thing on Twitter that kind of really took off. It was like I used the technique from Sony and Crane, the whole sort of sphere or what is it called? The Monte Carlo, their Monte Carlo PDE method. Their sort of it's not sphere tracing. What am I looking for? The term is walk-on sphere. Sorry. So I took their walk-on spheres technique that they used for basically geometry processing applications, and I used it along with basically some lessons learned from Veach's thesis to actually do walk-on sphere lighting using SDF luminaires. So that was kind of interesting. So there's these little ideas these tiny little ideas that seem to be really interesting that just sort of pop out of nowhere. It just takes, developing out a little more. In fact, Yining Carl Lee on Twitter mentioned that, walk-on spheres could have a serious application for, it would introduce bias, but still could have a very interesting application for subsurface scattering, multiple scattering beneath the surface, because the sphere travels above the surface just as well it sort of travels below the surface to find an exit point. So that could be really interesting for multiple scattering. Still, I feel like it might be biased, and few share that opinion still, but building that out and saying, okay, here we can do sort of diffuse lighting, here we can also use it to do subsurface scattering. I've actually reached out to Peter Shirley. I haven't heard back from him on the subject, but I would like to sort of bug him more when the time comes to kind of perhaps maybe develop these out, in further detail. And yeah, it could turn into a really nice write-up. It's about sort of isolating these little ideas and building out on them, right? This technique in particular just has a ton of knobs, and the sort of the gap filling is that tiny little thing that I feel like can be built out on. It's about just isolating these little things and building out on them.
Yeah.
That would make for a great article.
Yeah, no, bug Pete again. He's one of the editors for Ray Tracing Gems too. So
cool.
Busy guy, but that might be like he may have some advice. I mean, like right now they're basically sort of taking proposals and just sort of saying, yeah, you might want to go with that, or we got to start an article on that, or whatever. I don't know what they have as far as this kind of stuff goes, but I'm guessing not very much, because it's it's an interesting area that I'm fascinated by it, just because I like sort of seeing where different kinds of surfaces and so on, or different kinds of we've got voxels, we've got implicits, we've got whatever, trying to figure out how to exist nicely. Everybody's doing subdivision. Okay, fine. What else is there in the world?
Right. And sometimes the best things come out of hybrids, right? Like, it's like these things. Like I, for example, when I reached out to Peter, he had never thought of, like, basically before Keenan Crane's and Sony's paper, no one had actually considered walk-on spheres as for rendering. And the thing is that they took inspiration from Markov chain, Monte Carlo Markov chain processes for rendering. And
okay, folks, we are gonna conclude the poster session. That's only the televised part of this session. But you can stay as long as you want. Some folks have a very nice conversation, so I'm not gonna interrupt them. I encourage the authors to go and visit other posters and chat with their respective authors. Also, that's our social area, so you can stay and mingle with other folks about other topics. Finally, there are some folks that gather feedback for a survey, so you can also chat with them if they want to ask you some question about your experience. I'm particularly interested in what are gonna be their findings. And with that, I'm signing off and hand over the stream to the conference chairs probably.
Okay.
Let me speak with Eric. He's here. So,
I have a question.
hi Eric.
Yeah, sure.
Hello.
Can you conclude this day of I3D?
So when you
you want me to sign up?
Yeah.
I don't know what this is.
Basically an extension of uniform grids. So this is like the the oldest trick in the book, essentially. It's a uniform grid, and you basically are building it out by
We're probably going to do it virtually this
running
time.
over the primitives and finding
Or should I do it instead?
Boxes, putting in references, and you just basically cast a tiny ray segment. It's not exactly a watertight trace. It's like the ray segments are basically the size of the edge of the voxels, and they basically just travel through space and they check each cell. And if it's all if the first reference they encounter is blank, it's an FFFF, they'll just keep going until something gets not, and then they'll just iterate through the references and do triangle intersections. So that's basically.
So you're tracing through voxels.
Okay.
It
seems that I'm gonna conclude this day of I3D. So let me look at the schedule so that I can give you an idea about what is gonna happen tomorrow.
I mentioned that they do exactly
so,
the same thing. Except they also use geometry proxies to deal with very highly dense scenes, and I basically use my gap-filling technique to avoid doing that.
All right. Tomorrow we have a keynote by Julian Petre and posters. No, you can always visit posters whenever you want. So this area is gonna stay open. We have paper 6, characters and crowds, and paper 7, which is capturing the real world. So that's pretty much it. And hope you enjoyed the poster session. Stay safe, and I'm signing off. All right.
Basically my way of getting to the second floor.